Welcome to this fourth and final part of this mini school. So today we will explore phase transitions and critical phenomena at surfaces and interfaces in colloid polymer mixtures. And we will also deal with fluctuation effects. Up to now, as you recall, we have treated mean field. We've treated the system in mean field approximation, largely ignoring fluctuations. And now we're going to, today we're going to include fluctuation effects. And this will open up for us a more sophisticated avenue. And as a consequence, we'll have to moderate our exercises and homeworks because the calculations involved are more substantial and therefore cannot easily be integrated in a mini school. It would be possible to do it in a meso school or a macro school, of course, but this is not what we have at the moment. So let me introduce also the co-workers in this camp. Dirk Aerts, Henk Lekkerkerker, Yves Hannequin, Yves van de Kan, Jesper Koning, and Daniel Bon. So welcome to the world of colloid polymer mixtures. These papers can be consulted. They underbuild the presentation that I'm giving today. And so the main emphasis will be on the fluctuation forces and wetting layers. And we will also discuss the notion of interface potential, which is like a constraint free energy, not very different from the one we've seen recently when we discussed the free energy at the fixed wall value for the order parameter. And the use of this interface potential will permit us to discuss the line tension, the excess free energy associated with the contact line where three phases can meet in a non-wet configuration. So here we go. So the first part will deal with colloidal suspension. It will start it up from sort of 19th century type of thermodynamic considerations and the kinetic theory of heat and the origins of statistical mechanics, Brownian motion and things. Then we'll go to the discussion of a system that is effectively a hard sphere system, to which we will add tunable attractions in order to have interparticle forces that are repulsive at very short separations and attractive at larger separations. We'll discuss the scales in this colloid polymer system and compare the scales with those that we're used to in classical molecular fluids. Then we describe functions and variables that are of interest for us, and then go on and attack the walls and wetting properties and discuss the free interface. Remember the plus-minus interface, or the alpha-beta as we called it. We'll discuss also fluctuations, thermal fluctuations on that interface, which are called capillary wave fluctuations and which may or may not roughen the interface. And then we'll go to the wetting discussion, so the unbinding transition from a wall. And we'll also address renormalization group predictions and compare those with experimental data. And finally, we'll devote whatever time we have left to one of my favorite topics, which is the line tension. So let me check online whether everybody is on board. I don't see big problems. I don't see problems in the chat either. So I assume that we're all in business. Good, so we go back to the presentation. So Colloidal suspension. So what are we considering? Well, we're considering mesoscopic particles in a solvent, or you could say dust particles in air, or little, very tiny little balls in a fluid. And such suspension can be stable, or it can be unstable. And when it's unstable, it may, for example, sediment, and everything collapses onto the bottom and forms an aggregate at the bottom, and game over. But here we are interested in stable suspensions, and in those circumstances, the colloidal particles that are mesoscopic, 1,000 times larger, or maybe 10,000 times larger than atoms, they dance, driven by the random collisions with molecules or atoms in the solvent, according to the kinetic theory of heat. And there are many scientists that were involved in the 19th century. And I just, because I'm from Belgium, I mention just Thirion, Delceau, and Carbonel, who were Jesuit priests, and in their useful time, they were doing science, and they also, together with colleagues in other countries, proposed that these colloids are driven by these random collisions in a very well explored way that we now call Brownian motion. And as many of you know, the theory and the experiments on Brownian motion have provided the definite proof, final convincing evidence to every scientific person that our matter is composed of atoms and molecules. Now, in order to have a stable suspension, we need the particles to roam around, to dance around, in spite of the fact that they're a little bit heavier than the surrounding fluid. And so if they were not thermally agitated, they would sink to the bottom and form an aggregate. So there's a criterion that I like to call levitation by agitation, and that is represented by the value of a dimensionless quantity, so just a number. And this number basically is a ratio of, you could say ratio of whatever, but in this representation, I prefer to think of it as a ratio of energies. And one energy is typical, the gravitational potential energy difference of the colloidal particle being traversing a vertical distance of the order of its own diameter. And its own radius is called RC, R of the colloid. G is the gravitational acceleration. M is the mass of a colloidal particle. And M fluid is the mass of a fluid that would occupy the same volume as a colloidal particle. So MC minus MF is the buoyant mass. And so this, may I call it buoyant energy, if the buoyant energy is less than the thermal energy, then the thermal wandering or the thermal agitation will permit the particle to remain in flight, so to speak. And the suspension will be stable. So that will be the case when the Peclet number, that's this PE here down here, this Peclet number is less than unity. And the Peclet number actually has a very sensitive dependence on the radius of the colloidal particle, actually radius to the power 4, because there's a radius to the power 3 here in the mass. And so this Peclet number is of all the unity typically for particles that have sizes of about a tenth of a micron, so typically speaking. So good. So we have our colloidal suspension here that is supposedly in a kind of equilibrium. And what are we going to do to it? We're going to treat it in a sort of very harsh way, because the first thing we're going to do is we're going to adsorb a certain kind of polymer, not shown here, onto the surfaces of these colloidal particles. And this absorbing polymer, we will assume that it's already present in the particles that we have sketched here in this drawing. So this is the colloidal particle already coated with some sort of an adsorbing polymer. And by this coating, we have basically rendered these colloidal particles to be analogous to billiard balls. So we have largely, say, prevented the particles from sticking to one another. But still, these particles will have some kind of longer ranged interaction with one another, say van der Waals interaction, or maybe there could be other forces, but we will assume that we have only van der Waals interactions between them, so the particles can be chosen to have just that. But even then, we would like, first of all, to eliminate those attractions that exist between those particles. And this we do by matching the solvent properties to the colloidal particle properties. So basically, what we're going to do is we're going to match the static dielectric constant of the solvent with the static dielectric constant of the colloids. And we're also going to match the refractive index in the visual, so frequency-dependent refractive index. We're going to match that in solvent and colloidal particle. As a result, the net van der Waals forces between those colloids will be negligible. We also have, as I said already, we don't have other forces here present, like the LVO and so on. These particles are now, to a very good approximation, just billiard balls that randomly travel throughout the system in Brownian motion manner and that collide with each other as billiard balls. So good, but this system is now a hard sphere system, and that system has been studied a lot and does not have properties like the ones we are going to introduce here. Which are properties that that rely on the existence of a hard core, plus also some short-range attractions. Because with these short-range attractions present, we can obtain very nice phase equilibria and critical phenomena in bulk that we could not obtain by having just hard spheres. Although hard spheres can show some sort of phase transition, but not a critical point, for example. We would like, in fact, to go to a system that is described by the Ising model. So short-range interactions in a three-dimensional system, and short-range in the sense of strictly finite range, in fact. And so if we would succeed in that, we would be able to study a system which, from the point of view of universality and critical phenomena, would be described by the Ising model. And in three dimensions, the Ising model has very interesting interfacial and surface properties, as we will discuss further. But we're not yet there. We're going to introduce in the system some non-adsorbing polymer, and these particles are sketched here, with a radius of gyration that is comparable to the radius of the colloidal particle. And both amount to diameters of the order of a tenth of a micron. Now, what happens if we introduce a polymer concentration in the solvent? So the polymers can go everywhere, except they cannot enter in the excluded zones about each and every colloid particle. And the excluded zone drawn here, this dotted line, is a zone into which the centers of other colloids cannot intrude, and also the centers of these more or less spherically spherically configured polymers also cannot intrude in those excluded zones, because the gyration radius is comparable to the colloid radius. So there's an excluded zone here, and now the interesting point is that if the excluded zones of two neighboring colloids have an overlap, then the polymers cannot anymore go in between those two colloids. And they will be excluded from a certain overlap volume. And because they cannot intrude anymore between two colloids as soon as there's an overlap of excluded zones, there is an osmotic pressure effect that will try to push the two colloids closer together than they already are. And this we could call an osmotic pressure effect, as we already did, but we could also call it a depletion effect. So the overlap volume is depleted of polymers, and so in fact the polymers experience a slight increase in the available volume in the system when two colloids approach each other so closely that the excluded zones will overlap. And so this is an entropic advantage for the polymers. And so we could call this overlap of excluded zones as, say, the instigator of a depletion attraction between colloidal particles caused by the impossibility of polymers to go there in that zone. And this interaction, this depletion attraction, is of strictly short range, because if you bring the colloids a bit further apart so that the overlap volume is 0 and the excluded zones are distinct, then the polymers can again go in between them, and there is no depletion attraction at all. So this depletion attraction corresponds to an energy between the colloidal particles that is a potential energy that is in fact here, drawn here, and that is negative and finite, and then goes to 0 at some particular distance. And in fact, this distance is related to the size of the polymers, to the molecular weight of the polymer. Because if we increase the radius of gyration, then of course we will effectively increase the excluded zone around each colloidal particle in which the polymers cannot enter. And so this is the interaction that we had hoped to be able to introduce, which is the short-range attraction. It's an energy. It can be written as the volume times the pressure, and the pressure is, of course, not surprisingly, the osmotic pressure of the polymers. So this interaction is called the depletion attraction. It was proposed by Asakura, Osawa, and Vrij. And if we look at this in the particle potential now, we can say, well, this is, say, a short-range repulsion plus a short-range attraction. And the features of this interaction potential are the same as the features of any sort of short-range interaction fluid or lattice gas model or an Ising model, in which there is a strength of nearest neighbor attraction energy proportional to this osmotic pressure and proportional to the concentration of polymers. The more polymers we put here, the stronger this effect is. And this, of course, is a quantity which typically we could call epsilon, which is the well depth of the attractive potential, the short range attraction. And we also have a range, as we already said, which corresponds, roughly speaking, to a nearest neighbor distance in an equivalent lattice gas model or Ising model. Now, typically for all these models and for all these systems, molecular fluids, the ratio of epsilon to KT is of order unity at the instance at which phase separation and criticality do occur. So typically epsilon over KT is of order unity for a critical point for molecular fluids or binary mixtures. Epsilon over KT is of order unity for the triple point as well. And so, so this ratio of order unity will indicate the capability of the system will correspond to the capability of phase separation into two phases. One phase will be analogous to a liquid, and it will be a phase that is rich in colloidal particles. And the other phase is a phase which is largely depleted of colloidal particles, therefore is rich in polymer. And so the phase separation in this system is very analogous to the phase separation of a lattice gas. Okay, where a particle corresponds to colloid particle and the vacancy corresponds to absence of a colloidal particle, and therefore lots of space for the polymers to go in. Okay, great. So we have the possibility here to study a system that should be well described by just the three-dimensional Ising model. And why that is interesting will be revealed rather soon. Let us first go to a pedagogical survey or investigation of the scales in our system. We'll see that the scales here are very different from those in classical molecular fluids, and therefore lots of direct observations become possible of certain thermodynamic quantities that in molecular fluids are only indirectly observable. Let me go back to see if there's something going on in the chat or if there's some questions. There's some questions. Maybe there's a good time to post them. Let's see. We have several attendees at the moment. We have also panelists. So let me pause for 5 seconds and check that there are no questions. Okay, that does not seem to be the case at this moment. So let's go back and reveal the amazing differences in scales between our colloid polymer mixture in the solvent and ordinary molecular fluids. As you notice on these pictures, there's a portion that is in fluorescent green and a portion that is not. And so these colloidal particles have been coated with or provided with some properties that permits them to shine fluorescently and to be so that the colloid rich phase is predominantly fluorescent. So that's an additional trick that was applied. And you can see very well that in this tube, we have two phases. One is richer in colloid than the other. And the region close to the glass cylindrical wall has been shown here in some detail. And we see that the meniscus is rising against the glass wall, and the scales are such that the typical length scale over which the interface is curved before it stays completely flat, as it must be due to the gravitational forces, is of the order of less than 100 micron. That already tells us something interesting, because if we would do this with water or coffee in a cup, we would typically get 0.5 millimeter for this length instead of this much smaller length. And so that's one property we're going to look at. And this property is called the capillary length. And the capillary length is defined as the ratio of the interfacial tension between these two liquids and the gravitational acceleration times the density, the mass density difference between the two liquids. and the square root of that. And this will turn out to be micrometers for colloids and millimeter range for molecular fluids. Now, how does this come about? What can we say about the interfacial tension? What can we say about the density difference, mass density difference? As it turns out, the mass density difference between these two liquids is not much different from an ordinary liquid mass density. So there's nothing really strange going on there, but there is something spectacular going on at the level of the interfacial tension. So let's go to that. The interfacial tension in this system is a kind of energy. Now think in terms of bonds between particles. Particles attract one another, and if they come close, there is an energy gain of epsilon per bond. But of course, there's also an area to be considered. So we have particles at an interface or at the surface. So there are broken bonds because above them there are less particles of their own kind, whereas below them, in the liquids that they belong to, there are many particles around of their own kind. So we could view the interface as a kind of a forest of trees of broken bonds that stand perpendicular to the interface, and each of the trees brings an energy cost epsilon in the picture. And so we have an energy cost of epsilon per square diameter of the colloidal particle, because that's the area that one particle takes in at the interface. And so if we now look at this epsilon, so remember this epsilon, in order to have phase separation phenomena, critical point and two-phase coexistence, this epsilon's got to be something like KT. And the sigma, however, is around 1,000 times larger than that for regular customary atoms and molecules. So we're going down by a factor of 1,000,000 in surface tension, in interfacial tension. So that's a bit alarming, you could say, because then the interface will be wobbling about in a much more drastic way than a molecular fluid interface would, and that's happening. And this is very interesting because by virtue of this rescaling of the interfacial tension by a factor of 1,000,000, we're going into the nanonewton per meter range instead of the millinewton per meter range as for water against air, for example, which is around 70 millinewton per meter. And by virtue of this lowering of this interfacial tension, the interface fluctuations, the thermally agitated wanderings with an A, not an O, well, also O, of course, because it's a miracle. But the wanderings with an A of the interface are so important that they can be seen by just ordinary visual microscopy, which is not possible for molecular fluids. So the thermal agitation of the interface, which is measured by comparing the KT thermal energy, T is absolute temperature, of course, divided by the interfacial tension, the square root of that, is the typical excursion the interface will make by thermal agitation with respect to a horizontal plane. Now, I don't know if this is going to be possible to see this here. No, sorry about that. I thought that there would be a movie behind this, but of course there isn't because I didn't arrange it properly. So, well, in this case, you see that the wobblings of the interface excursions in a direction perpendicular to the reference horizontal plane are of the order of a tenth of a micron for colloids. And so they become detectable in just ordinary microscopy, say using ordinary visual light. And in contrast, they're only about an angstrom in linear dimension for molecular fluids. So only the interface for molecular fluid would with a visual microscope would not be perceived as being wobbling, but would still be perceived as extremely flat. So interface fluctuations called capillary waves of all sorts of wavelengths conspire and become directly measurable, directly observable using just ordinary microscope. Good. So we have explored spatial scales here. We have explored interfacial tension scales. There's also a time scale to be explored that will come a little bit later. And now we go to functions and variables. Now, let's see if we have everybody still on board here. Yes, indeed. Okay. No questions at this moment. Good. So which functions and variables are we going to consider? Well, we will have to consider some sort of a free energy, a sort of a bulk free energy. And for this system at hand, it is very instructive to consider the solvent as a sort of a background, to consider the colloidal particles as the main actors here from a particle point of view, and to consider the polymers, the non-adsorbing polymers that have been added as a kind of a gas-like background that penetrates everywhere possible in between the colloids. And importantly, for this system, we must assume that, of course, the colloids are impenetrable mutually, so they are like billiard balls. And also the polymers cannot penetrate into the colloidal particles, of course. So we will consider the colloids and the polymers as impenetrable. However, we consider for this simple description that the polymer particles themselves can interpenetrate. So they do not feel any sort of hardcore repulsions among each other. So this is like an ideal gas background. The polymers form an ideal gas background in the system. Now, the semi-grand canonical potential, as it is called, consists of the Helmholtz free energy of the colloids at temperature T, volume V. So the volume is indicated here on the left. Okay. And there's a number of colloids present in this volume, which is called NC. Now, there is a semi-permeable wall here that permits polymers to go across, but not colloids. The colloids are confined to the volume V, whereas the polymers can go in and out, and we can tune the concentration of the polymer by tuning the chemical potential of the polymer in a sort of reservoir that is in contact with our actual system. And so we assume ideal polymers, and so we assume Van 't Hoff's law, ideal expression of equation of state for these polymers, and that is that their partial pressure, called the osmotic pressure, is the number of polymers per unit volume, so the number density of the polymers in the reservoir, which is the number density that that we can tune, times kT. So that's the osmotic pressure that the polymers exert. Now let's be careful, because the density of polymer in the system is of course a lower density, because the polymers cannot use the entire volume, but must stay out of the excluded zones, excluded by the colloids. So the number of polymers in our system is the density that is dictated by the reservoir times the volume that is available to the polymers. And that is called the free volume. Now, the free volume can be estimated in a very crude fashion as follows. we can say this is the volume of the system minus the volume of the excluded zones. But now the volume of the excluded zones, what shall we take it to be? Well, if we would assume that the system is very dilute in colloidal particles, so that the excluded zones do not overlap, then for each excluded zone, we could say we have a volume that is 4/3 pi times radius to the power 3, and the radius would be composed of the colloid radius plus, say, plus a certain range that into a first approximation would be the radius of gyration of the polymer, assuming the polymer is a little ball that is rolled up and that has this typical characteristic linear size. So that would be a first guess, but of course, this guess has to be corrected, not only for subtle configurational refinements at the level of the polymer itself, but also because the excluded zones will overlap when the colloid concentration or the colloid volume fraction increases. And so this will open up some extra free volume for the polymers. And so this is an important consideration. So we could say that the alpha fraction that we have introduced depends on the colloid volume fraction, and also depends on the ratio of this extra length that is polymer related to the colloid radius. And the alpha will in practice be less than this 1 minus the colloid volume fraction, because the colloid volume fraction would amount to set this delta equal to 0, which is of course not correct, which is of course an underestimation of the excluded volume. So the volume fraction of the polymer is less than the volume fraction of the polymer in the reservoir, and is reduced by a factor of alpha, which takes into account that the free volume is substantially less than the total volume. So we have, in sum, we are dealing with excluded volume interacting polymers. Now here is a graph that already contains a lot of information concerning phase separation, concerning criticality, concerning interfacial tension. So the points that are experimentally studied and for which we also try to do calculations are these systems S1, S2, and S3. And S1, S2, and S3 lie on what is called a dilution line, which can be explored by, as it says, by diluting the system, both in colloid and in polymer simultaneously. So this is a typical experimental circumstance in which we can explore systems on a dilution line. Now, on this dilution line, phi polymer and phi colloid, respectively, the volume fractions of polymer and of colloid are proportional to one another. And what you can see here is that system S1 is more concentrated, and therefore is farther from the so-called bimodal line, which is the phase separation line for this system. If we go to very low polymer and colloid concentrations, we have a single phase fluid, and we're above criticality, so to speak. Whereas if we have a more concentrated system, we have the possibility of phase separation. And so this should be seen in the context of what we have said before, the epsilon, the well depth of the colloid interaction part in interaction energy, the epsilon is of order kT when we do have criticality and phase separation. And if the epsilon would be much less than that, because we have not enough polymer, not enough colloids, then we would have predominantly just a single phase state, and the attractions would not be strong enough to induce phase separation. So that's fine. So here is the bimodal. Here is the say presumed critical point that's say can be inferred from properties of the system and from theoretical calculations, which would give one that is nearby. And here are two quantities that we already mentioned. One is the interfacial tension, and you see that it is of the order of nanonewton per meter, and it goes down to ultra low values of about just a few nanonewtons per meter for the system close to criticality, where the two phases, the colloid concentrated and the colloid diluted phase, are almost identical to one another. And so the interfacial tension is extra low there because it goes to 0 at criticality. And for the other systems, it's still ultra low, but it can go up to about 100 nanonewtons per meter for S1. The width of the interface, remember, is characterized first and before all by the thermal length. So basically, it's a kT divided by the surface tension and the square root of that. And so the surface tension, or let's call it interfacial tension here, when it is ultra low, we would get, of course, a significant interface wandering, interface wobbling of amplitude of about 1 micrometer even, right? And for the system S1, it would go down to something like about half a micrometer. So these are typical properties being concretized here for our mixture, which we discussed in terms of the scales of the system. Good. Now we go to our main target, and that's wetting properties of this system. And we will try to relate these properties to everything we have learned before in the preceding hours of this mini school. So we'll come back to the Young-Laplace equation. We'll come back to the contact angle. We'll come back to the sigmas, which are called gammas here. So the interfacial tension between plus and minus phases, or liquid and gas, and the wall tensions, wall against liquid, say wall plus, and wall against gas, wall minus, surface tensions. We'll come back also to our density functional theory in its Kahn, Landau, de Gennes form, and we'll even encounter the analogues of surface field and surface enhancement for this system. And at the same time, we will explore experimental observations using a rather beautiful technique of laser scanning confocal microscopy. So using visual light here and scanning through the system, probing the density of colloids in successive planes perpendicular to the line of sight, as we focus at increasing distances from the glass wall into the mixture. So let me go back a second to the chat. Okay. So if you want me to stay awake during this talk and this lecture, you better start considering asking questions at some point, okay? Good, I count on you. So give you a few seconds there. Coffee also helps, of course. So let's go back to our core business. Okay, here. So good. So our core business is walls and wetting, of course. And where shall we start? Well, let's start here from the picture. So the scale here is given below. It's 350 microns, consistently with the capillary length of the order of 70 micron that we encountered a little bit earlier. Here we see the colloid rich phase and the colloid poor phase, and we see that the meniscus, or the interface between them. There's a question. I'll interrupt now for a question. Thank you so much. So, okay, hang on. Yeah. So I can read the question maybe. Do we neglect the intramolecular forces for ideal polymers? Can we consider phase separation as when the colloid precipitate out? Aha. Okay. So well. Thank you for these two beautiful questions. So let me go back to the pictures here. So this picture will be the best one. So first question is, do we neglect intramolecular forces for ideal polymers? Well, to some extent we do. So in this first step approach, we assume the polymers to be just basically like little balls that can interpenetrate and that cannot interpenetrate with the colloids. Okay, so this is of course well, rather crude, but still it will permit us to obtain already some reasonable agreement with experimental properties, experimentally measured properties. If we would go beyond that, we would go in the direction of the protein limits. The protein limit would be when the size of the polymer, or the radius of gyration of the polymer, is much larger than the size of the colloid. And then we can conceive all sorts of things. We can conceive, of course, different configurations of the polymer. We can consider that polymers can wrap around the colloids. And we would need a more refined description, which is available, and which certainly would be very important to check. And we will address this issue a little bit later if we have time today, when we discuss the contact line and the line tension, and the contact angle measurements of a three-phase contact zone. But we do not consider these things now here, so we assume indeed that we neglect all sorts of interactions that are intramolecular. We neglect configuration changes of the polymer. We just consider them to be balls that are mutually transparent, but not transparent relative to the colloids. Now, the second question, I think, well, I cannot see it here on the screen, but the second question, if I remember well, is do we consider some sort of phase separation, including the aggregation or the precipitation of the colloid? No, we don't. So here we assume that the colloids are in equilibrium and float around in the solvent so that we have a stable suspension that does not precipitate out. Regardless, or I should say, nevertheless, the phase separation that we study is one in bulk, which has nothing to do with sedimentation, but which is close to an ideal sort of liquid-liquid or liquid-gas phase separation. that you would have in a binary liquid mixture, or you would have in a liquid vapor system. And one of the phases is slightly denser than the other, and therefore sits at the bottom, and the other one sits at the top. But there is no sedimentation or precipitation out here of these suspended colloids. So thanks, Jane, for those questions. Maybe there are other questions now also. Let me check. Okay, yeah, good. So back to our presentation. So here, excuse me, here. So in this picture, we recognize the pure Young-Laplace equation and the mechanical equilibrium of the contact line. The wall here is a vertical spectator phase, okay, and the adsorbate is just these two liquids. And so the Young-Laplace equation reads that the gamma, which we previously called sigma in our previous lectures, the wall surface free energy against the gas. So in particular, this particular at this height, we would be talking about the gamma wall gas. At this particular height, we would be talking about gamma wall liquids. And this interface has an interfacial tension gamma liquid gas. Of course, liquid and gas are metaphors. The gas is also a liquid, but is poor in colloid. And so from that point of view, it's a colloidal gas, if you like, compared to the other phase, which is rich in colloid particles. And theta is, of course, this contact angle here. Now, we know that we can set up Kahn-Landau density functional theory, which permits us to calculate these three interfacial tensions. And if we can calculate those three interfacial tensions in a model where there is just one spatial inhomogeneity, that is to say, we use a spatial coordinate perpendicular to this surface here. Also here we use the spatial coordinate perpendicular to this surface to calculate this excess surface free energy. And here we use a coordinate which is now vertical and which is perpendicular to the liquid gas interface in order to calculate that interfacial tension. But having calculated those three, we can extract the cosine of theta, which we could call the cosine of a thermodynamic contact angle that is defined through mechanical three-phase equilibrium. And that is not necessarily equal to the one that is observed here in the experiment. Of course, ideally it would be, but this will, in practice, not be the case. But we hope that the approximation is reasonable. So this model has been developed by our colleagues, and they found that there is a wetting transition for this system such that under the circumstances at hand here, we should have a complete wetting state. So we should have a contact angle that is 0. Okay, now this is of course not visible here. And the reason that is not visible here, of course, is multiple. First of all, this is a rather crude sketch on top of a photograph. And we haven't explored different scales of length in order to see down to which small length scale a contact angle can be meaningfully defined. But that's not the point. The point is that the cosine of theta here in this Young-Laplace equation is by definition a thermodynamic quantity. And the question is whether that thermodynamic quantity is unity or is less than unity. And that distinguishes the wet from the non-wet states. So the determination of a wetting transition is a thermodynamic problem, okay? And the observation of a contact angle, a measurement of a contact angle is actually a different, you could call it molecular or you could call it geometrical problem. And under the circumstances of these experiments, it is believed, and it is also consistent with experiment, that we have complete wetting. Now, this is seen quite directly in the pictures on the right that I will explain in a second. But let us come back first of all to the Kahn-Landau theory and identify the quantities that we have learned in the previous sessions of this mini-school. You will recognize that there is the gradient squared of the order parameter. And so this term penalizes variations in homogeneities in the order parameter. The coefficient of this gradient squared is a quantity which, close to the critical point, is approximated by a constant. Here it's still represented as a function of the number density of the colloids, or the volume fraction of the colloid, which is proportional to that. And the rho here is the order parameter of our problem in the density functional theory that we use. Now, there are several questions here. First of all, what is this M of rho really about? And it is really about a direct correlation function in the system. It's dependent on that, and in such a way that indeed close to criticality it is constant, or perhaps it could have a very subtle singularity, but that falls outside the scope of our description. So we will say that it's a constant for our purposes. And this quantity here, you will recognize, it used to be called f of m previously, and now it's some f of rho minus some chemical potential for the colloids times the order parameter plus some pressure, some reference pressure. And it's actually an excess pressure that when you draw it as a function of rho, because of its composition in these different terms, it will be precisely a double well potential with equal minima, with two equal minima below the critical point of this system. Below the critical point, of course, is a way of speaking, because in our phase diagram that we had just before, we are here above the critical point in volume fractions. So this is like an f of m that we had before, and this is like a c times dmdz squared that we had before in our Landau theory for wetting, Kahn-Landau theory. So there's not much new here, but now you'll say, but wait a second. This is the colloid volume fraction, or we could say the colloid concentration, okay, colloid density. What about the polymer density? That should also enter, and maybe it's an independent order parameter. Well, the good news is that it's dependent on this order parameter, and therefore it must not be included explicitly in the description. Why is it dependent on this colloid volume fraction? Well, let's go back here. So basically, the polymer volume fraction is this alpha times this fraction times the reservoir polymer volume fraction. Now, the reservoir volume fraction is controlled by the chemical potential of the polymers in the reservoir, and that is assumed to be constant. And in fact, I didn't tell you yet, I neglected to tell you when I talked about the semi-grand canonical potential, that there is, of course, the Helmholtz free energy of the colloids, but there is also, when you do the integral over the number of polymers times the chemical potential, the chemical potential variation, you will find a result that turns out to be, in the ideal gas approximation for polymers, turns out to be kT per polymer times the number of polymers that are actually present in the volume V. And that number depends, of course, on lots of things, but it depends explicitly on the chemical potential of the polymers in the reservoir in the first place. So basically, we assume that we have fixed the chemical potential of the polymers in the reservoir. As a consequence, this volume fraction will be also fixed. And the alpha, note this fraction that the free volume is smaller by compared to the actual volume, depends on the colloid volume fraction and the geometrical parameter, which of course has to be calculated, which has to be calculated in what's called a scaled particle theory. It has to be calculated carefully. That enters in this free volume expression. So here we will assume that there is a certain fraction there, and dependent on that fraction, we can calculate the properties of the system. But you see that once this parameter and the reservoir chemical potential for the polymers is fixed, that the polymer volume fraction is also determined and dependent only on the colloid volume fraction. So this is the reason why in this theory there's only one density, one spatially varying density included for our wetting properties. Then the question arises, what is the surface field and what is the surface enhancement? Not surprisingly, the surface field has to do with the overlap of excluded volume of a particle, a colloidal particle coming close to the wall. So there are two excluded volumes. One is stemming from the wall. There's an excluded zone in which the colloids cannot enter. And that excluded zone has, of course, a width of the colloid radius. And of course, there's also a circular band of excluded zone for each colloid. And so the overlap of those excluded zones determines the surface field. And the situation is such that the overlap of excluded zones of wall colloid is greater than the overlap of excluded zones between two colloids. And therefore, the wall exerts an extra depletion attraction on the colloidal particle over and above that which another colloidal particle would exert on the tagged colloid that we bring close to the wall. So the H1 will be a positive surface field. And then there is the enhancement G, and I will be brief on that because, of course, it would cost long sentences to do this or a calculation. And the G has to do with the modification of the overlap of excluded zones when two colloids that are close together are also close to the wall. And we'll see that there is a reduction of the overlap of excluded zones between two colloids when they are close to a wall. And therefore, the G is a negative quantity, it's a de-enhancement, and therefore we will see properties that in principle could entail first order wetting or critical wetting. For this system, a first order wetting is predicted by an actual calculation. And as I already said, under the circumstances of our experiment, we are in the wet regime. We are in the regime where cosine theta equals unity. Theoretically, but experimentally, this is also consistently confirmed with these laser scanning confocal microscopy images. So here's the glass wall along Y. Perpendicular to it is the Z direction into our mixture. And here's the microscope objective. And using this technique, we can scan a certain plane at a certain distance from the glass wall, and we can go into the system, and two slices are represented here. One slice at the red arrow, and so now you turn your line of view by 90 degrees, and you look in the direction of the incoming laser light along that direction, and then you'll see this this view on your television. Okay, so this, what we see here is a slice along this direction. And in a perpendicular view at the lower end, we see the liquid like phase, and the upper frame. In the upper part of the picture, we see a denser phase, but it is actually we're inside the wetting layer. And as you can see here, the wetting layer is something that is spread out all over the wall and gradually thins as we increase the height relative to the horizontal liquid gas interface. So we're inside the wetting layer here, and if we go deeper into a liquid mixture from the glass wall towards the inside, we will see the liquid gas coexistence. We'll see a very dilute in colloid phase here and a rich in colloid phase down here. And we see the wobblings on the interface. Now the intensity, the fluorescence intensity reflects the density of colloids, and we can probe the intensity along the direction perpendicular to the glass wall and along the incoming laser. And so if we go into the system, we see this intensity very, very close to the wall is small because we're in the excluded zone. But then we go into the liquid-like layer, and then ultimately we go into the gas phase. So this picture corresponds to a scan which is more or less around this height here. If we take the derivative of the fluorescence intensity, we'll get this particular plot, which is permitting us to estimate the widths of the interfaces, the widths of the glass liquid interface, the width of the liquid gas interface at this particular height. In terms of fits which involve Gaussian functions, Gaussian probability densities. And the L that is depicted here is in fact what you could call the wetting layer thickness at a particular height. So let's say at this height here. And one of our objectives will be to study that wetting layer thickness as a function of height, because if we are able to do that, of course you cannot see it here in this picture, but you can infer it from this picture here. If we would be able to study the wetting layer thickness as a function of height, we would in fact be able to study the wetting layer thickness as a function of undersaturation of the liquid-like phase, because we have a saturated vapor at the height of the bulk liquid gas interface, but an undersaturated vapor if we go higher up. But we also have a wall which preferentially adsorbs the liquid-like phase. So we have a competition between an undersaturation component in the force that acts on this interface here, and an attractive component that promotes the adsorption of the liquid-like layer. So if we can study this, we will be able to capture the dependence of the wetting layer thickness on the so-called bulk field or undersaturation. And we can combine this study of the wetting layer thickness with the study of the interface fluctuations, the interface width, and the correlations along and perpendicular to the interface. And that is very interesting because a theoretical study of these properties in the three-dimensional easing model has revealed very interesting non-universal behavior, and has been the subject of decades of very sophisticated and compelling studies by several of our colleagues, notably into extreme detail and extreme rigor by Andrew Perry of Imperial College. And so let's go on here and discuss the interfacial properties in reality, in experiment, and also in sophisticated renormalization group calculations context, going beyond mean field theory, because mean field theory would normally only predict very smooth interface because it ignores such transverse fluctuations. Certainly the mean field theory we have used only takes into account inhomogeneity in one direction, the direction perpendicular to the interface, like this direction here, and does not take into account any sort of transverse fluctuations, which are not only beautiful, but also scientifically very important. So let me check for possible questions here. Okay. Also check for time. Okay. I see no urgent questions. So thank you. I will go back to the presentation now. So now we are really into modern theory and modern experiments, if I may say so. Remember that the interface between the liquid-like and the gas-like phases, which are actually two liquids in reality, can be studied progressively closer and closer to criticality, and therefore closer and closer to situations where the interfacial tension is ultra low and interface fluctuations become very important. So in 1 to 5, you see here different interface configurations depending on the distance towards criticality, and you see huge interface fluctuations here in the bottom picture. Now, what means huge? Well, there is the thermal length. The thermal length, which determines actually the width, the natural width of interface fluctuations, and this is the ratio of KT to gamma square root of that, as we discussed before. And so there are two opposing effects here. One is that surface tension, surface free energy would like the interface to have minimal area, so it does not promote any sort of wobblings or wanderings. But of course, the thermal agitation, provides energy and also provides many ways, many configurations. So a large entropy contribution to interface wanderings, and so will render a typically observed an observed interface typically rough. Certainly on the scales that we have discussed, which are here much amplified with respect to molecular fluids. Then there is the capillary length, and the capillary lengths you could interpret as a gravity penalty, because of course you can have interface fluctuations and interface going up and down like on an ocean, but gravity of course doesn't want this to go really out of hand, because the lower phase is denser in mass than the upper phase. So gravity will penalize those excursions and will tend to tell the interface to stay horizontal. And of course, if we would let gravity slowly disappear, we would obtain a very large capillary length, and then of course we would we would not observe these the tendency to stay horizontal, and the interface would really develop all sorts of overhangs and all sorts of steep wanderings. There is another length here that we can consider, which is a system size in horizontal direction, which we call Lx. So for this horizontal interface, one can study interface fluctuations using capillary wave theory, and this has been developed by many scientists in the past. And the upshot of this is that the height excursion relative to the horizontal average plane for the interface squared, averaged over thermal fluctuations, is averaged over a probability distribution that is governed by the Boltzmann weights, is proportional to this expression, which is not surprisingly the thermal length squared. So that sets the amplitude of this interface wandering. But there is a logarithm here, and that might be of concern, depending on what is present in its argument. Its argument is a ratio of length squared, or inverse length squared, rather. And this ratio features several of these lengths that we have discussed. So we have the colloid radius here, which actually sets a cutoff because we cannot have interface capillary wavelengths smaller than the colloid diameter. So that would be physically nonsensical. So to have a wavelength, you need at least a certain number of colloidal particles collectively having a displacement in the same direction. And so that's a microscopic cutoff for the waves. And then there is the capillary length, which is like a cutoff, actually a cutoff at the large system size end, which also will terminate long wavelengths fluctuations of the interface, because wavelengths much larger than the capillary length cannot occur, because over lengths larger than the capillary length, the interface has to stay perfectly horizontal. And so this gives us a window of wavelengths, and we find this window of wavelengths in a different way in the denominator here. In the denominator, there is here the system size. The system size, of course, would also limit the longest wavelengths, but could be actually quite large. So the contribution coming from the system size here could be of concern. But again, in a gravitational environment, the capillary lengths will cut off those long wavelength fluctuations, and for very large system sizes, in the denominator, the only remaining term would be the 1/4 capillary length squared. So that altogether, we can look at first of all, to get a good idea of what we're doing, we switch off gravity and we look at the interface that is fluctuating in a kind of unhindered way. So the capillary waves are not tempered by gravity at long length scales. And then we see what damage this logarithm can do, actually, because then we retain the logarithm of the system size divided by the colloid radius. So for very large system sizes, without gravity, the interface wanderings can lead to, at least theoretically, to a divergent width, so a divergent amplitude, which grows logarithmically with the system size. So this would mean that the interface is intrinsically rough on large length scales if we would not have gravity in the game. Now, this logarithmic dependence is typical for freely fluctuating interfaces in 3 dimensions, ignoring gravity. But interfaces fluctuating in lower dimensions than 3 have even more important roughness, because their height fluctuation squared will go as the system size, the parallel linear system size of the interface, to some exponent which is 2 times zeta, and zeta is the interfacial roughness exponent, as it is called. And for example, in two dimensions, we would just have 1/2 here. And so this would mean that the square root of this variance, so a standard deviation for the interface fluctuations, would go as the parallel length scale, the size of the interface, to the power 1/2. So it's the square root of this transverse length. And so the interface in 2 dimensions, the profile of it, height versus distance, would form a profile that is reminiscent of a random walk profile, which would be distance versus time. Also an exponent of 1/2. So interface wandering without gravitational stabilization leads to rough interfaces in dimensions below and at 3, whereas 3 is the marginal case with logarithmic roughness. So, so this is our situation coming from capillary wave theory. And to close the discussion on this slide, I mentioned that also the timescales, the timescales related to this system, timescales related to interface wanderings, to capillary wave fluctuations, are timescales that are favorable for direct visual inspection, because a typical timescale would be a viscosity times interfacial tension times a capillary length. And if you take these all together, you would obtain seconds for this colloid polymer system, whereas you would have only 10 microseconds typical timescale for molecular fluids. So how are these quantities determined? It's good to spend a minute to tell you about the experimental determination of, for example, the interfacial tension. The interfacial tension can be extracted from inspection of the height correlation function along the wandering interface as a function of space or time. So time or space correlation function for the heights, different distances at the same time and different times at the same distance. And the amplitude of those height correlations will give us information about the thermal lengths, and therefore information about the interfacial tension. Then the capillary lengths can be determined from the decay of the height correlation function for interface fluctuations as a function of space, and the relaxation time, tau, can be obtained from the information coming from the time-dependent height correlation function. So that's how these quantities can be measured in this system. So knowing now what the free interface is doing, we can go to an interesting question related to the wetting layer. So now it will become slightly more, how should I say, involved, but also quite exciting, because we will be able to say something about predictions of 3-dimensional wetting theory for short-range forces, like the Ising model, and also quantities that are extracted here from these observations. Now, let me go back to the here to see whether there is a question. Okay. All right. So let's go back to the wetting problem. So the wetting layer that is very visible here against climbing up against the wall, the thickness of the layer we can call L, and it depends on height. And we can also determine the width of the liquid vapor interface or wetting layer, the width of the wetting layer, the width of the interface of the wetting layer against the gas phase, so the wetting layer surface, which we call either W or we call it psi perpendicular. And we also can distinguish typical parallel distances parallel to the interface between excursions, between bumps of capillary wave fluctuations. And that is also a correlation length that we call psi parallel. And we will be able to calculate and measure these quantities and interrelate them. And that's where a lot of interesting physics is going to be revealed to us. So this is called unbinding from a wall, but unbinding is another synonym for wetting. So basically we have a wetting layer, which is due to the fact that the contact angle is 0, and so we have some amount of liquid adsorbed here. That's what the wall prefers. That's great. But we also discussed that gravity doesn't want this heavier phase to go very much up here. So gravity wants to thin this layer, and so we have a competition of two effects that we will try to characterize through a kind of interface potential that will govern the position of the liquid gas interface relative to the wall. So the height fluctuation characterized by this variance here, so the height minus the reference height or average height squared, averaged, is related to the quantity we discussed previously, but the difference is that now we are considering a vertical interface instead of a horizontal one. So for the vertical interface fluctuations, the gravity is not of direct consequence because those fluctuations are in a direction perpendicular to the gravitational acceleration. So we do not see the intervention of the capillary lengths here in these interface fluctuations, which are wobblings that are in the horizontal direction. Of course, there is the basic amplitude of the thermal length squared here, because it's squared of h, which persists. And there is also the logarithmic dependence that comes from capillary wave theory. And the logarithmic dependence, as you recall, has a dependence which involves a kind of a typical width of excursions or typical distance between interface excursions. So let's go back here. So gravity is of no consequence for the considerations for the vertical interface, but there is the analog of this Lx, but Lx is the system size, but the system size for the free interface is just the total available space in the direction parallel to the interface. But the system size in this situation where the interface is at a certain distance from the wall is limited by the parallel correlation length. And why is that so? Well, you see, if we would have interface excursions, then certainly these interface excursions will feel the presence of the wall. Interface cannot bump into the wall. And also the interface excursions will feel the presence of gravity, because the gravity doesn't want the interface excursions to go very far out, because the interface excursions are hindered by the undersaturation. So there is an undersaturation of colloids at this particular height. And at every height that you consider, there's a certain amount of undersaturation. And that undersaturation tells us that the liquid phase is not stable in bulk. and therefore interface excursions, which would tend to thicken this liquid layer, are disfavored by this undersaturation, which indirectly is determined by gravity. So there is an indirect effect of gravity that hinders interface fluctuations in this direction, and there is the wall which stops interface fluctuations to bump into it. And so there is like a corridor of a certain width in this distance perpendicular to the glass wall, the horizontal distance, a certain corridor into which the interface fluctuations are confined. And this is the interface potential well in which the interface sits. And this interface potential well introduces a finite width, a finite parallel width. So not only a finite perpendicular width, but also a finite parallel width that is relevant here. And so interface fluctuations will tend to repeat themselves, so to speak, once we go to lengths larger than this parallel length. And therefore, this parallel length replaces the system size for interface fluctuations along the vertical direction. And the colloid radius is the smallest possible wavelength of interface fluctuations. But if we are close to the bulk critical point, the liquid gas bulk critical point, in fact, the smallest cutoff for interface fluctuations is larger than the colloid radius, because bulk fluctuations will induce, say, a kind of fractal structure on small scales in terms of density fluctuations. And so there will be overhangs, and there will be, say, the interface will not be defined in terms of a single valued function anymore. If we go to length scales lower than the bulk correlation length, which might well be larger than the colloid radius, which might be 2 times, 4 times, 6 times the colloid radius maybe. So in order to have a complete description close to bulk criticality, which is of interest here for us, because we're interested in wetting properties and at very low interfacial tensions, so close to bulk criticality, because low interfacial tensions can give us significant interface wanderings and can give us significant effects of the confinement of fluctuations by the presence of the wall. So we want to be close to bulk criticality, and therefore we should anticipate to replace RC by the bulk correlation length in the following. Now, why is this so interesting? You see, interface fluctuations are confined here by the wall potential, by the wall interface potential. They're confined by the presence of the undersaturation, surely so, but they're also confined by the presence of the wall. So we could say that compared to a free interface that is freely wandering, here there are less capillary wave fluctuations that are allowed. So the entropy contribution to interface fluctuations is diminished. So there is an entropic, say, you could say an entropic repulsion, because the interface fluctuations are hindered by the wall. So we could say that there's a contribution of the wall potential that tries to push the interface a little bit away from the wall, because if the interface would want to go a little bit away from the wall, it is rewarded by having more space for excursions. And so its entropic term in the free energy becomes more important. And so its interfacial or surface tension, say, will get actually lowered if it goes a bit further from the wall, okay? Because its fluctuations then become more free. And so this effect of the wall is called entropic repulsion. And the effect of the entropic repulsion is something very exciting to study quantitatively. Why is that so? Well, let us now have a look at this. The wetting theory for 3D, for the 3D easing model, for short-range forces, for transitions that are of continuous character, and these include critical wetting, which are not studied here because this is a first-order wetting transition that is somewhere in parameter space. But we are in the complete wetting regime. And that means that as a function of undersaturation, turning the undersaturation to 0, approaching a two-phase coexistence, and this can literally be studied here in this band. You see, in this band, we're actually going to approach two-phase coexistence, and the wetting layer thickness in the horizontal direction will grow. And this approach to complete wetting, or infinite wetting layer thickness, macroscopic in reality, is called the approach to complete wetting. And the approach to complete wetting is hindered by the undersaturation. So the theory as a function of undersaturation is equivalent to the approach to complete wetting for short-range forces in 3 dimensions. And this theory has features that are very analogous to the theory for critical wetting transitions, because in both phenomena, the wetting layer thickness diverges in a continuous manner, not in a jump-wise way, but in a continuous manner as we vary, say, under saturation, or as we vary temperature, for example. And so in this wetting theory for continuous transitions, there is this parameter omega, which is a number, and which measures the thermal length relative to the bulk correlation length. And as you go close to criticality, the interesting thing is that this LT, which is KT divided by the interfacial tension, okay, is such that the interfacial tension itself becomes of the order of KT per square correlation length. So the relevant area, the relevant unit of area for interfacial tensions close to the critical point, which give you a finite number when you consider the ratio of, say, interfacial tension on the one hand, and KT divided by correlation length squared on the other hand. That ratio is this wetting parameter omega, which attains a finite value at criticality for the easing model. Now, for the easing model, this value is about 0.8, not far from 0.8. And so this is interesting because this is a value that has a certain, say, specific significance. And in the renormalization group theory, which is a theory that takes into account fluctuation effects in models and in reality, and that takes into account the existence of universality classes and describes systems in terms of that classification, predicts that the wetting layer thickness, which is this distance L here, that's the thickness of that liquid-like layer, divided by the bulk correlation length, is this number here, times the logarithm of this parallel correlation length divided by the bulk correlation length. So the unbinding of the interface from the wall, which is the increase of L as we reduce the undersaturation, okay, is driven or drives, you could say, the divergence of this parallel correlation length. This is logical because as the interface thickens, it becomes more and more like a free interface where interface wanderings are no longer say, aware of the far out presence of a wall, and so this parallel correlation length can then diverge, and the interface wanderings can become say uncorrelated over very large parallel distances up to the system size, basically. So this is a very interesting dependence, but there is more than that. In this theory, the width of the interface here of the wetting layer against the gas phase squared is this particular number here times the product of two lengths times the transverse the thermal length and the basic amplitude of standard deviation of capillary waves times the wetting layer's thickness. Now, how does this come about? Well, this comes about by combining this relation here for the dependence of the parallel correlation length on the wetting layer thickness with this relation, which tells us that the width of the interface squared, which is nothing else but this psi perp squared by definition, is related to this LT squared times the logarithm of psi parallel over RC being replaced by the bulk correlation length if we are close to criticality. So the combination of this equation and this equation will give us this equation. But this is a very curious equation because it tells us that for a given distance to criticality, for certain thermal lengths, that the width of the interface squared goes as the wetting layer thickness. Now let's think for a moment what that would mean. Okay, suppose we would have a system in which the interface potential would be such that only the interface would only feel hindrance from the wall extremely close to the wall. So that's called a hard wall interface potential. If we would have such a system, then of course nothing would prevent the interface wanderings to go all the way to the wall and to have interface bumps that have a specific width that would be comparable to the wetting layer thickness itself. So the interface wanderings could go all the way down to the wall. If that would happen, that certainly would be an interesting situation. We could call it a strong fluctuation regime, where the wall potential is nothing really special, and the entropic repulsion would be just a very simple hard repulsion. And then we would have simply that the width of the interface squared would be proportional to wetting layer squared. Okay. And the converse situation, which also would be very typical, is that capillary waves would be negligible, that the interface would be smooth, that mean field theory would be right, or that the forces would be of certain long range to such an extent that we are not in a fluctuation regime and that we are in a kind of a mean field regime, possibly with logarithmic correction, weak logarithmic dependence. But in such cases, the width of the interface squared would just saturate to a constant, independently of wetting layer thickness becoming large. So in that case, the interface would be smooth. So those are two very typical situations that we would expect in practice in many systems. But this system, which, as we said, experimentally tries to mimic pure Ising model properties, which are ideal model-wise, because we can calculate so many things in that model and can go into so much detail there. This system, perhaps if experiment confirms it, would display a width interface width here that is proportional to the square root of the wetting layer thickness. Very curious. Now, what does the experiment say? Well, this is what the experiment says. So the blue is for the system S1, rather far from criticality, not so many data because interface wanderings are quite restricted. This is S2, and then S3 has many more data here. There's sort of serpent around a little bit here, which is a bit disturbing because we don't know what's going on in as far as that particular aspect goes. But certainly there is something here to say, because if we fit to these points, just experimental data fit, we would get this solid curve here, which follows very nicely this square root type of behavior, and which tells us indeed that that for small wetting layer thicknesses where we have certainly a strong confinement of interface fluctuations, the interface width is very much reduced. And then we approach the micron size interface width only for larger wetting layer thicknesses, but we approach this in such a way that the width is proportional to the square root of the wetting layer thickness, with this prefactor, which is a length, which corresponds, as you see here, to this prefactor times the thermal length. The theory that we have used to calculate this quantity using the input parameters that are available, which are essentially the interfacial tension, which are essentially capillary lengths, and which are essentially also the bulk correlation length, deduced indirectly from the assumption that omega takes this value, which is a reasonable assumption for this model under these circumstances. The theory gives something not far from what the experimental fit gives. If we ignore this wiggle, which we at the moment have no good explanation for, but the overall trend is well captured also by this theoretical result, which is the dashed line here. So let me go to the chat and see whether there is panic in the audience, and this is fortunately not the case. And so let's go back to our presentation. Well, these results, I emphasize again, they are surprising, see, because as I said, in mean field theory or in some sort of long-range forces, van der Waals forces systems, in many models and real systems would show that the interface width approaches a constant when the wetting layer becomes very thick, and that in fact the free interface would also have very weak capillary wanderings and have a finite width. So that would be a very typical situation. Also very typical would be that, well, the wall potential would be of strictly short range and would have a strictly finite range, even not even exponential decay or something like that. And this would entail a lot of, this would correspond to a lot of systems that can be considered, also realized experimentally to some extent at least, and that would have so-called strong fluctuations. So all fluctuation regimes, in fact, would predict that the width of the interface would be just proportional to the wetting layer thickness, and that interface wanderings can reach the wall and hit the wall and then rebound. And so this is true for all dimensionalities less than the so-called upper critical dimension for wetting. And regardless of whether you have short or long range forces, regardless of whether you have critical or complete wetting, and including membranes, including the physics of membrane fluctuations. So that will be the width proportional to the wetting layer thickness. But what we have here is the width proportional to the square root of the wetting layer thickness. So not, say not just any power, but just power 1/2 between 0 and 1 of potential theoretical possibilities. And so this is a very special behavior that we are able to probe on the one hand theoretically, if we study short-range forces exactly in 3 dimensions, for which we achieve the upper critical dimension for critical and complete wetting transitions. And as I explained, the experimental system, which was tuned, which was tailored, which was manufactured to be consistent with this type of short-range system in 3 dimensions in the class of the Ising model. In the universality class to which the Ising model also belongs, this system experimentally shows this behavior, this square root behavior, quite convincingly. And so that's quite remarkable that a colloid polymer system was able to that one was able to devise this colloid polymer mixture in such a way. Now, we have some 10 minutes left. I'll try to give you a little bit of a flavor of a few things now. The interface displacement or interface wanderings in the presence of a wall can be described by a density functional theory that is reminiscent of the density functional theories we considered before. But the interesting point here is that in this case, we are integrating over the directions parallel to the interface, and our order parameter is the height variable of fluctuations of the interface coordinate, if you like, or collective coordinate, perpendicular to its surface of average position. And so this is another type of functional that is called an effective interface Hamiltonian, describing the energy cost of interface fluctuations perpendicular to its common positional plane, to its reference positional plane. So we have the gradient squared of the interface displacement as a function of the parallel coordinates, and it is multiplied now by the interfacial tension. Not surprisingly, because if we have a gradient squared, we also have an increase of interfacial surface, right? Interfacial area, and so that is penalized by this interfacial tension coefficient. And the remaining part here is a kind of an interfacial energy, which is the wall potential. It's called the wall potential. So that wall potential will favor interface displacements that amount to a compromise between the interface being repelled by a wall by this entropic repulsion, and interface being called back to the wall by undersaturation in bulk, so that the thickness of the wetting layer is limited by the undersaturation of the wetting phase relative to the phase in bulk. And so this wall potential, as a function of some sort of an average value of the wetting layer thickness, would include this gravitational, in this case it's gravitational, penalty of the undersaturation, and also the entropic repulsion, which tells the interface to go further from the wall as far as possible in order to maximize its entropy, in order to take advantage of the possibility of having larger interface wanderings before it hits the wall, or to have larger interface wanderings before it comes too close to the wall. So here, on average, we can say that we can obtain a kind of a mean field expression for this wall potential, but then including fluctuations, we call the result a renormalization group calculation for the interface potential, and it would be an average over interface fluctuations. Now, what do we mean by interface fluctuations? Well, you see, self-consistently, we can say the interface has a certain width, which we call W, which maybe we'll be able to find out what it is. And that interface is free to wander in a sort of a corridor, say at a certain average distance from the wall, which is the average wetting layer thickness. And the width of this corridor is, of course, the width of the interface, the wandering interface. And we average the wall potential, the mean field potential, over a distribution which is a probability distribution that is Gaussian and that is centered about the average position of the interface, which is the L bar, which is the wetting layer thickness in mean field approximation. And so this averaging amounts to a renormalization of the mean field interface potential. So we take into account that the interface, although its average distance from the wall is L bar, has some probability to be at a different distance from the wall. And this probability distribution is Gaussian and has a certain width. So that averaging amounts to the result, that is the renormalized interface potential. And not surprisingly, as long as we have a linear function of the wetting layer thickness, it just reproduces this mean field contribution. But with a nonlinear function, we get a modification of the amplitude of this exponential repulsion, which is the entropic repulsion of the interface by the wall. And interestingly, this amplitude does have implicitly a dependence on the wetting layer thickness, because the wetting layer thickness has a dependence because the wetting layer thickness is dependent on the parallel correlation length, which enters here in this calculation, which enters through properties related to the width of the interface, which, as we have seen, is also related to the parallel correlation length. As we may recall, there is this dependence here. Which is L depends on the parallel correlation length, but then also the xi perp, which is the width, depends on L. Okay, so there is and here it is even more explicit. So here's xi perp squared depends on xi parallel in a logarithmic square root of a logarithm, actually, for 3 dimensions. Okay, and so here this amplitude will actually diverge when the wetting layer thickness increases. And so this counteracts, this opposes this exponential decay to some extent. So the decay length of the exponential decay is actually modified, is renormalized by interface wandering, by thermal fluctuations. And so that's an interesting point. Now, see, we don't have much time left, so let me go a little bit further. If we include this knowledge and the modification of this decay length by a parameter that involves omega, then we can infer the wetting layer thickness dependence on the height along the vertical glass wall. As we go higher up, we increase the undersaturation. And so we'll have a decreasing wetting layer thickness as we go higher up. And theory in two different forms, one is more sophisticated and the other more correct than the other, predicts these two very, very closely separated curves to be compared with the experimental curves. But remember, the experimental curves, they exhibit a wiggle that we cannot capture here, or we cannot explain by the theoretical considerations that we have used. But at least we could say that there is some qualitative agreement. And these are the results for the other temperatures, but when we're farther away from criticality, the interface wanderings become less important, and then the assumptions underlying the theoretical calculations become weaker and weaker and much less satisfied. So there is a discrepancy here that should not worry us too much, and there is some kind of we could call it incipient agreement with the experimental data, at least at some sort of a qualitative level. But this is still very remarkable because this dependence on the height of the interface, you see, is extremely difficult to measure because try to equilibrate this system, when do you really have equilibrium? How long do you have to wait? So these are very, very important, painful questions. that must be asked. And so the status of these experimental data, of course, as a theorist, I should speak for myself, not speak for the experiments. So I'm going to stop here and say that theoretically we cannot quite capture the behavior of these measured points. Now. Oh, so well, maybe this is a beautiful point to add to end the talk and to end the mini school. So what I would like to talk to you about, but cannot anymore, is the behavior of the what's called the line tension at wetting. So the free energy associated with the contact line. The excess free energy associated with the contact line where three phases meet. And so three phases could be like here, a wall type of phase, like the bottom of this aquarium, and then here the liquid-like, and here sort of a vapor-like phase. And they would meet at the common line of contact called the contact line, of course. And associated with this contact line is an excess free energy per unit length. And that has the same dimensions as a force. And in reality, the force could be something like of the order of nanonewtons, or could be perhaps of the order of piconewtons, as could be calculated, perhaps also measured. And this is a beautiful subject with its own critical exponents, its own type of scaling laws, and so on, which I have devoted a lot of time to in my career, and cannot devote much time to here in the mini school. So thank you very much for your attention so far, and let me check whether there are questions. Yeah. Okay. So I understand that everybody is still there and is recovering from the fluctuations in this mini school. So are there any questions at this point? I don't think so.
Hi, Prof. Yes, there's a couple of questions in the chat.
Oh, yes. Oh, in the chat there. Oh, yes. Thanks. I'm looking in the chat, but oh, here. Yeah, I'm okay. I should. Oh, just a second. Trying to, but it's also here. Yeah, thank you. Do you oh, there's a question from Dr. Joseph Kirui. Oh, thank you so much, University of Venda. Are you still there? Are you there? You can unmute yourself if you wish. I'll answer the question in any case. It is, do you or any of your research colleagues study surfaces that do not involve wetting? I mean surfaces and interfaces found in solar cells between layers, for example, active layers, electron transport layers, and hole transport layers. So that's okay. That's a question from Jane, I think, isn't it?
No, that is my question. Prof.
Oh, it's your. Oh, thank you. It's your question. Well, you see, well, one of the surfaces that that we study in a context which you could call a more general interface context, not necessarily wetting transitions or anything like that, but you see, when you have contact between surfaces, contacts between phases at surfaces or at interfaces, then as soon as these phases have some kind of liquid character, as soon as they can flow, you naturally encounter the situation of whether they are in direct contact with one another or whether they are excluded from having direct contact with one another. And so this is very important, for example, when you make metal matrix composites, in order to produce filters for all sorts of purposes. And it's also very important if you want to if you want to produce surfaces that you can use in micro and nano electronics, because there you want to use surfaces that can be cleaned. It can be cleaned under certain, say, with certain regularity or for certain practical reasons. And so you want to use certain liquids on those surfaces, and you want to permit those liquids to intrude, or maybe not intrude, depending on the application between the microcircuited channels or the structures that you have implemented. And so for those purposes, you want to construct surfaces that have, say, micro or nano pillar structure that would prevent certain liquids to stay just on top of the pillar heads, or other liquids to go in between and maybe remove certain microscopic or nanoscopic contaminants or objects that could be there. And so so the question whether we can study surface interface from point of view that is not a wetting point of view is similar to the question whether you can ride a bike when you're blindfolded. So it certainly is possible, and you could, using your ears and maybe some other device, you could certainly avoid getting into problematic situations. But of course, the information that you could gather by just looking and seeing where you're riding your bike is comparable to the information that you would get, say, when you bring liquids in contact with one another, or you bring liquids in contact with solids, when you are permitted to measure or calculate interfacial tensions, right? So
yes. So okay, in that situation, where what would contribute to the tensions? Because I understand if liquids are involved, we are mostly talking of surface tensions.
Yeah, so well, for liquids, we can have interfacial tensions in terms of the energy of broken bonds, as I explained for the colloid system. For solids, we have to be much more careful, because for solids we have elasticity, and we have contributions to the interfacial tension, which are the following. So basically, an interfacial tension or interfacial free energy is basically the coefficient of the area in an expression of the total free energy, which has a volume contribution, area contribution, line contribution, point contribution, and so on. But we must be very careful, because we will have an interfacial tension, and we also have a surface stress. And basically, the derivative of the free energy with respect to area would be equal to the coefficient of the area in the interfacial free energy, plus the area times the derivative of that coefficient with respect to area. And so there is an elasticity effect, in that the surface tension must be distinguished from the surface stress as soon as we have solids. And so this is very subtle, and this is a very interesting point of attention. And we also must distinguish between directions in space, because we will have different sort of surfaces, differently oriented, like in crystals. And for different orientations of the surface, we'll also have different say, unit areas to be considered. So the density of atoms per unit area is different in those different surfaces which have been cleaved from a solid. And so all those considerations amount to complications that are not present in fluids. I don't know if this
yes, no, you have answered.
Useful.
Thank you so much, Prof. In future, of course, we can trace it back we can raise you and get help where necessary. Thank you so much.
You're welcome. Yes, you're welcome. I think there is
Thank you.
another
Thank you.
question. Okay, not involved wetting, yes. Then here, oh, there's a, I see, is there another one there? Or did I already discuss this? Yeah, there's a question like surface science of solids talk a lot about dangling bonds and tetrahedral holes and octahedral holes. Does the model take these into consideration already? Well, no. Say the models I discussed assume that the interface or the surface is a single valued function, and so does not take into account any sort of cavities or any sort of overhangs. Those can be taken into account, but when you go into this regime of overhangs, you go into the description of fractals, and then you have a fractal dimension which replaces the bulk dimension of the system, and you will have properties that are if you want, say, reminiscent of bulk properties in a system of modified dimensionality. So between 2 and 3, for example, dimension between 2 and 3. So the models that and the theories I'm discussing ignore those sorts of effects, and they have a lower cutoff in the wavelength of capillary waves, which is of the order of the bulk correlation length. Because on length scales above the bulk correlation length, we can speak about a single valued function for the interface. So we can have self-affine interfaces or flat interfaces. Thank you very much for that question. Okay. So I think it requires your finger to. So I think that I've covered the questions here, and I am very grateful for this opportunity to have given you this mini school, and I wish you all a very nice continuation of your scientific and beyond scientific futures. Okay, bye-bye.
Yeah, thank you. Thank you, Prof. Bye-bye.
Bye-bye.
Thank you.